Section: Introduction. In this section, we build upon recent advancements in video diffusion models, which have evolved significantly due to breakthroughs in foundational image models. These models, trained on extensive datasets like WEBVID10M and Panda70M, can create realistic and diverse videos from text or image prompts. Beyond just generating high-quality content, we note that these generative models are also being used as feature extractors for various analysis tasks, such as matching and segmenting images. Interestingly, even though they are trained on 2D data, image generators have shown unexpected capabilities in 3D tasks. This leads us to question whether pre-trained video generators exhibit similar 3D awareness. To explore this, we focus on the structure from motion (SFM) task, which involves understanding scene geometry and how viewpoints change across frames. A recent development, Dust3R, has shown that the traditional optimization method for camera estimation can be replaced by a network trained to find correspondences between image pairs. We observe that the architecture of the VIT backbone in Dust3R shares similarities with the diffusion transformers, DIT, used in leading video generators. This motivates us to investigate if the intermediate features from a DIT-based video generation model, specifically OpenSora, can be utilized for camera pose estimation. To support our research, we introduce a new architecture that combines video generation with camera pose estimation, which we call Joint Generation and 3D Camera Reconstruction, or JOG3R for short. This unified model can generate videos, estimate camera poses from videos, or perform both tasks simultaneously. We conduct a comprehensive study on these tasks within the JOG3R framework. First, we examine if the features from the video generator inherently possess 3D awareness by routing raw features to the camera pose estimation heads. Next, we explore if these features can be further refined for better camera pose estimation through fine-tuning. Our experiments reveal that while the video generation features show some inherent 3D awareness, additional supervision during fine-tuning significantly enhances this awareness. This improved supervision leads to competitive camera pose estimations compared to state-of-the-art methods, without compromising the quality of the generated videos. We propose a network that jointly generates videos and establishes correspondences, promoting more consistent 3D results. Although the visual quality may not surpass that of standard video generators, our approach excels in 3D consistency. The primary aim of our paper is to investigate the 3D spatial awareness of video diffusion models, specifically assessing how well features from existing video models can be used for camera tracking. We also seek to determine how much better tracking can be achieved with fine-tuning and whether we can maintain or enhance video generation quality. In summary, our contributions include extensive experimentation on the utility of video features for 3D camera estimation and the introduction of the first unified model capable of both generating videos and estimating 3D camera positions, which we refer to as JOG3R. In the related work section, we note that the research community has successfully adapted diffusion models for video generation, building on their success in image synthesis. Early adaptations involved adding a temporal dimension to image diffusion architectures, allowing training on both image and video data. Typically, U-net-based architectures have incorporated temporal attention blocks and expanded 2D convolutions to 3D. To reduce computational demands, latent video diffusion models have been developed, operating in a lower dimensional latent space. Additionally, some research has focused on generating high-resolution videos through cascaded pipelines, which include keyframe generation, frame interpolation, and super-resolution modules. Recently, there has been a shift from U-net-based architectures to using the diffusion transformer DIT backbone, which processes space-time patches of video and image latent codes. Our method is built on OpenSora, a publicly available DIT-based latent video diffusion model. Section Summary. In this section, we explore the advancements in video diffusion models, particularly focusing on their potential for 3D awareness and camera pose estimation through our proposed unified model, JOG3R, which integrates video generation with camera tracking. Our experiments reveal that while video generator features show some inherent 3D awareness, fine-tuning them significantly enhances their performance in camera pose estimation without compromising video quality. Section 3D Reconstruction. In this section, we discuss 3D reconstruction, which relies on well-established principles of multi-view geometry, such as extracting features, matching them, and using triangulation with epipolar constraints. These methods help us create accurate but sparse 3D point clouds and estimate camera positions from multiple images. We have seen improvements in the efficiency of 3D reconstruction through techniques like linear time incremental structure from motion and hybrid approaches that refine results from coarse to fine. To enhance robustness against outliers, we can apply global camera rotation averaging and optimization methods that utilize features from points that vanish with oriented planes or from learned neural networks. These techniques help us avoid issues related to rotation and scale drift. We also focus on global camera pose registration and joint estimation of 3D point positions to improve scalability and efficiency, especially for image sequences with small baselines. Once we have estimated camera poses and sparse 3D point clouds, we can use multi-view stereo to generate a dense 3D surface. This can be achieved using either handcrafted visual features or neural features, along with a cost volume to predict depth estimates that are globally consistent. Existing neural rendering methods help us reconstruct dense surfaces by modeling cost volumes and using differentiable rendering for photometric supervision from multi-view images or monocular depth estimation. Some methods eliminate the need for camera calibration, allowing us to optimize at test time for a consistent depth map without knowing the scale or poses, using a fixed depth prediction model. We can also integrate unsupervised signals from dense correspondences, like optical flow, to learn from unlabeled data. Recent advancements have introduced a direct regression framework for dense surface reconstruction from pairs of images, where we learn to predict coherent depths and camera parameters or directly generate per-pixel 3D point clouds from two views using vision transformers with dense tokenization techniques. Next, we explore the use of a generative diffusion model, which is trained on millions of paired images and text prompts, developing a meaningful visual prior. We are interested in leveraging this strong prior for various 3D vision tasks. By incorporating 3D awareness into the diffusion prior, we can significantly enhance the accuracy and generalizability of tasks like monocular depth estimation and correspondence search. We often use latent features from a pre-trained diffusion model as a backbone, training a task-specific decoder with cross-attention for various applications, including semantic correspondences and 3D pose estimation. However, we note that these image diffusion features do not account for the temporal relationships between frames, which can lead to unstable 3D predictions from videos. To address this, we propose using video diffusion features as a backbone for multitasking predictions related to video generation and 3D camera pose estimation. For our model, we consider OpenSora as our base video generation model, which is a diffusion model that operates in a lower dimensional latent space defined by a pre-trained VAE encoder. Each frame of the input video is projected into this latent space. During the diffusion process, we add Gaussian noise to the latent code incrementally, resulting in noisy latents. Our denoising model takes these noisy latents, the time step, and a text prompt as input to predict the added noise. For camera pose estimation, we utilize the Advanced Multi-View Stereo Reconstruction Framework DUST-3R. This framework independently encodes each image using a VIT encoder, allowing two decoders to process the features and share information across views. We then estimate point maps and align them to determine the relative camera pose using Procrusta's alignment. Finally, we apply a global optimization scheme to register multiple views from the same scene as a post-processing step. Section Summary. In this section, we discuss advancements in 3D reconstruction techniques, highlighting the integration of multi-view geometry and neural networks to enhance accuracy and robustness in generating dense 3D surfaces from images. We also introduce a video diffusion model for multitasking predictions, which leverages temporal features to improve camera pose estimation and depth prediction in video sequences. Section: Unifying video generation and camera reconstruction. In this section, we propose a unified framework that connects the video generation process with camera pose estimation. We notice that both VIT and DIT share similar designs as they are part of the transformer family. Our main idea is to swap the image-based VIT encoder in Dust3R with the video DIT backbone from OpenSora. In this approach, we send the intermediate features from the denoising DIT network to the Dust3R decoders and heads. Specifically, we take the output from a certain block of the STDIT network at a specific time during the reverse process. We focus on small time steps, which help capture low-level details useful for matching features across frames. For our modifications to Dust3R, we extract features from a sequence of frames and provide them to Dust3R in pairs. During training, we ideally pair the first frame with all others, but due to memory limits, we sample 4 pairs to predict 3D point maps. At inference, we predict point maps for all pairs and refine the camera pose, depth, and focal length for each frame, similar to bundle adjustment. Since we are working with a sequence rather than sparse views, we add 2 new terms to the global registration objective to promote smooth camera movement and consistent focal length between adjacent frames. These terms are only used during inference. For training, we focus on 2 main objectives: generation loss and reconstruction loss. The generation loss aims to match the added noise, while the reconstruction loss measures the difference between predicted and actual point maps across valid pixels and frames. We explore how different combinations of these losses affect performance. Specifically, we analyze the effects of using reconstruction loss alone to assess the 3D awareness of the video features, and we also test a combined loss to see if the features can be adapted for both tasks. In our experiments, we evaluate 3 tasks: video to camera, V2C, text to video, T2V, and text to video with camera, T2V plus C. For V2C, we add noise to an input video, denoise it, and then route the features to Dust3R for camera pose estimation. For T2V, we assess how camera pose supervision impacts video generation quality. In T2V plus C, we generate video and camera data simultaneously without needing to reprocess the noise. We use OpenSora 1.0 as our video generator, which includes a 2D-VAE, a T5 text encoder, and an STDIT architecture for denoising. We freeze the first 4 STDIT blocks and only update the temporal attention layers in the remaining blocks. We extract features from a specific block for Dust3R. The last 2 blocks serve as a generation branch, updated only by the generation loss. We also experiment with different decoder structures and find that a single decoder with full 3D attention performs comparably to a duplicated structure. During training, we sample time steps for noise addition and compute losses using empty prompts for reconstruction and video captions for generation. At test time, we sample time steps for camera estimation and provide outputs to Dust3R for joint estimation and video generation. Section Summary. In this section, we propose a unified framework that integrates video generation and camera pose estimation by routing intermediate features from a video generator to the Dust3R model, enhancing both tasks through shared architectural elements. We detail our training objectives, which include generation and reconstruction losses, and describe our experimental setup for evaluating video-to-camera and text-to-video tasks, ultimately demonstrating the effectiveness of our approach in generating videos alongside camera parameters simultaneously. Section: Experiments. In this section, we evaluate our design choices in 2 key areas. We use standard methods to assess the quality of the generated videos and validate the accuracy of camera pose estimation on real videos. Additionally, we present results for generating videos alongside camera pose estimation, focusing on self-consistency since there is no ground truth available. For our setup, we select the Real Estate 10K dataset, which contains about 65,000 video clips with camera parameter annotations. We utilize the provided captions and adhere to their train-test split. During pre-processing, we compute the latent variables of the video frames and the text embeddings of the captions. We randomly sample 16 frames from the original sequences, choosing a frame stride from the options of 1, 2, 4, or 8, and we have a 50% chance of reversing the frame order. To create point map annotations, we estimate metric depth using Zoe depth, convert it to 3D, and align it with the first frame's coordinates using the camera parameters from Real Estate 10K. All camera parameters are referenced to the first frame. We also include the DL3DV10K dataset, which has camera annotations, as an additional test set, selecting 70 random videos for testing and captioning the first frame of each. Since no existing method can perform both video generation and camera pose estimation together, we compare our approach to task-specific methods. We use the original pairwise method Dust3R with a linear head and a global structure from motion method called GLOMAP for camera pose estimation as references. For Dust3R, we consider 3 variations, one with off-the-shelf pre-trained weights, one initialized with pre-trained weights and trained on our data, and one trained from scratch with our data. In all cases, we apply our new temporal loss functions during the final optimization step. For video generation, we use the pre-trained OpenSora as a baseline. To validate camera tracking quality, we compare the estimated camera poses with the ground truth poses. For rotation, we calculate the relative error between 2 rotation matrices. Since translation estimates can vary in scale, we compute the angle between the normalized translation vectors. We report both the average of these errors and the percentage of camera pairs with rotation and translation errors below a certain threshold. Given the small number of frames processed by our video generator, we set a threshold of 5 degrees for reporting accuracy metrics. We also calculate the mean average accuracy based on angular differences. In our reconstruction evaluation, we compare camera pose estimation errors on the Real Estate 10K test set and report errors for the withheld DL3DV10K. Our findings indicate that even when using decoders trained for reconstruction, freezing the Sora backbone results in poorer outcomes compared to trainable models. This suggests that raw features from pre-trained video generators are not sufficient for accurate camera pose estimation. We observe that models trained without generation loss yield similar results to our full model, indicating that maintaining generation capability has a limited impact on reconstruction quality. Our method, JOG3R, outperforms pre-trained Dust3R on Real Estate 10K, and when trained on the same data, it matches the reconstruction quality of the from-scratch trained Dust3R, but not the one with pre-trained weights. This implies that the pre-trained Dust3R weights hold more valuable information for camera pose estimation than those from OpenSora. Overall, our results suggest that JOG3R may not generalize as well, likely due to the faster motion in DL3DV10K. The pre-trained Dust3R methods perform better in this dataset because they have learned from matching wide baseline view pairs. We also report results from GLOMAP, which generally surpasses most methods except for one variant of Dust3R. This highlights the effectiveness of optimization-based methods. We visualize our camera trajectories and the correspondence between the first and last frames, showing that our method produces good camera paths, often closer to the ground truth than those from methods focused solely on reconstruction. Section Summary. In this section, we evaluate our design choices by assessing video quality and camera pose estimation accuracy using the Real Estate 10K dataset, while also comparing our method, JOG3R, against task-specific baselines like Dust3R and GLOMAP. Our results indicate that JOG3R outperforms pre-trained methods in reconstruction quality, although it shows limited generalization on faster motion datasets like DL3DV10K. Section: Generation Evaluation. In this section, we evaluate the generation of videos. For each method, we create 180 videos using captions from the Real Estate 10K test dataset and measure the FID and FVD against real images and videos from the same dataset. Our findings indicate that our complete model produces more realistic outputs compared to the pre-trained OpenSora. When we remove the generation loss, we notice a slight decline in quality, which makes sense since the absence of this loss means the model lacks motivation to fully utilize its generation capabilities. We also note that one of our baselines disables the reconstruction loss by removing certain decoders, making it similar to standard diffusion model fine-tuning, but only updating the weights of the temporal attention layers. The removal of the reconstruction loss affects the FID and FVD differently, leading us to conclude that camera pose estimation has a mixed effect on video generation. We provide examples of videos generated by our method, JOG3R. Next, we discuss the self-consistency between two approaches, T2V to V2C and the tightly coupled T2V plus C pipeline. We ran both methods with 100 prompts and found a small average difference in rotation and translation, suggesting that the camera poses from the joint pipeline are consistent with the other method. Our qualitative results support this finding. We also explore the synergy between the two tasks in our unified architecture, which allows for multitask training with generation and reconstruction losses. However, we observe that the generation loss does not significantly enhance camera pose estimation, and the reconstruction loss has mixed effects on generation. Thus, we conclude that there is no clear synergistic effect between the two tasks in the Open Sora 1.0 framework. Despite the lack of observable synergy, we still include the generation loss in our full method because it yields comparable camera pose estimation results and enhances generation quality. Finally, we highlight the value of JOG3R, as it is the first method to jointly perform video generation and camera pose estimation. Our unified architecture allows for end-to-end training of both tasks, paving the way for new research opportunities. While we can only compare with state-of-the-art methods dedicated to each task, we achieve competitive quantitative results in Real Estate 10K, and our qualitative assessments confirm that JOG3R generates realistic videos, estimates good camera paths, and maintains coherence.